okay? If an object is sitting still, we'll go ahead and use, it's a small object, but if it's sitting still, it's going to stay sitting still, unless something pushes it. Okay, like, oh, that makes sense. The other thing Newton said is if something is in motion, okay, if something's going dun, 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 you know, in motion like that, it's going to stay in the same motion. That would include both the direction and how fast it's going. It's going to do that forever, unless something else acts on it. Which here on Earth, that's kind of hard to prove a little bit, because if you push something, you know, eventually this pen will stop because of friction, the force of friction, and it will also stop because actually there's the force of gravity that's pulling it down. So actually, if we would look at that motion, it's got friction and it going against the motion, and it's also got gravity going kind of perpendicular to the motion. But he's pretty smart, and he's true. If you're in outer space and you toss accidentally a hammer or something like that, that thing in outer space has no friction, it has no gravity, although one of the things we're going to talk about is Newton's universal law of gravity, which basically says any object, if there's a hammer, and if there's a planet way over there, okay, there is a mutual attraction between those two masses, the masses being the hammer and the planet, all right? Okay, but that hammer's just going to go on and on and on. Newton says it's going to tumble forever, okay? Actually, that leads us to something else. Sometimes Newton's law is referred to as the law of inertia, okay? So we'll talk about that here in a minute. But so, for instance, the whole old trick up there in the purple where you have the quarters and you pull the thing out, okay? The reason the quarters stay there when you pull that out is because the quarters are at rest. They're going to stay at rest, okay? Just because you're quickly yanking out that purple sheet of paper, they should stay there. We say the quarters have a certain amount of inertia. The other things I brought in for this are Stonehenge. Certain amount of just, it is where it is, okay? It's not moving, it's not going to move unless you apply some force, okay? Let's see if this video plays. Now that I think about it, I'm not sure how pertinent this is. I just thought it was a cool video. Short. Haven't played any videos. That is weird. Okay. Let's try this. There it goes. Law of inertia. So my next slide deals with inertia. Okay. Newton's first law, the law that says an object in motion will stay in motion, an object at rest will stay at rest unless acted upon by another force, is also called the law of inertia. What inertia is the tendency, bless you, the tendency for an object to keep doing what it's doing, okay? Be at rest or move. So, inertia, if an object is moving in a straight line, it will continue to move in that direction with that same velocity, okay? Now, inertia is related to the mass of the object and the speed that the object's going. So those quarters had a certain amount of inertia related to the mass of the quarters and the fact that they weren't moving. Those rocks that were in that rock slide had a certain amount of inertia based upon the mass of the rocks and how fast they were moving. So here we have two people. That older gentleman right there, that's going to be me in a few years, having my kids push me. Just kidding, kind of. Two people in a swing, you know, one larger adult and a child. So the more massive the object, the more inertia it has. Makes sense. If you kind of think of the lady who's pushing both her grandfather and her daughter, okay, she's going to have to apply more force to move the father than to move the daughter. When that father is moving, he's got more inertia than the daughter. The more mass, the more inertia. Here's another one for you. I got a couple of figures off the internet. So Newton's first law says that an object that is stationary will stay stationary unless acted upon by an outside force. Now here's what happens when you are in a bus that's stationary. Okay, you're not connected to the bus, right? But the bus has a motor. Okay, the bus is going to start to move. I bet you do this. You're standing up just like that guy standing up. Okay, you're here. The bus is stationary. The bus is going to start to move, and you don't have a motor. You didn't get the signal. You basically are going to want to stay where you are. So as the bus moves, you're going to go like this. The bus is moving this way. You want to stay where you were. Of course, eventually you catch up with the bus, okay, and then you ride along with the bus. Then actually, as the bus is moving, okay, you have the same speed as the bus does, which means, though, the bus has brakes, you don't have brakes. Which means, though, if the bus is moving and the bus suddenly runs into something, well, you keep going forward because that's where you were going. That's Newton's law, first law of motion. And then that's when the bus, this is what you feel when the bus takes off this way, okay? And just like I said a minute ago, this is what you feel when the bus suddenly stops and you keep going. Okay. Don't have the brakes, didn't get the message. Okay, his second law of motion can be expressed as like a little formula. And I picked a homework that you can do for Monday to kind of get used to plugging in for these, the F and the M and the A. So according to his second law, you can kind of think of it a couple of ways. I like to think of it as, all right, you're gonna poke something, you're gonna give it a force, okay, and it's gonna result in an acceleration. So I kind of like to think of it. We talked about how you can take F is equal to ma and kind of rearrange it, okay. So let's see. I like to kind of think of it this way. If we want to get acceleration by itself, we can divide both sides by mass. Does that make sense? I'm going to divide both sides by mass. And when I do that, I can rewrite this. My masses have canceled. And I can say that force divided by mass is equal to acceleration. So I don't know. It's a thought. So that means that whatever force you push something with, okay, divided by its mass, you're going to see it go faster. And it's almost like and there's more to physics. I'm kind of just taking the highlights. There's like how long you apply the force. But just a poke, okay, divided by the mass, that's how much faster it's going to go. A lot of times it goes from 0, okay, to a certain speed, back to 0 again. Okay, we're not going to kind of talk about the other friction and gravity. Okay, but acceleration. Okay, so an object will accelerate once you poke it with a force, and it's related to its mass. So I mentioned the whole, remove friction, to remove the effect of gravity, let's go to outer space, right? And actually not that long ago, maybe it might have been 3 or 4 years ago, just the other day, there was an astronaut, and I believe it was a female astronaut, working on the International Space Station, and she lost one of her, like a hammer, okay? She lost one of her utensil things. And so you don't get a second chance at something like that. How many people have seen the movie Gravity? Yeah, that's what kind of reminds me of, where you're just kind of like, okay, time to go buy a new hammer. Actually, this slide is showing you his third law of motion, which basically says for every push that way, okay, the guy was pushing that way, there's another push this way on him from his hammer. Okay, basically you kind of see those 2 arrows going back. Okay, But in the meantime, the force that he poked onto that wrench, okay, we could go ahead and see how that wrench went from 0 speed to a certain velocity, and that's the acceleration. But we would calculate just like we did on the board over here. Don't forget how we calculate acceleration. A, or average acceleration, is the final velocity of that wrench minus the initial velocity, it was probably 0, divided by the time, okay, over which that acceleration occurred. Okay. So F is equal to ma means that the strength of the force is equal to, you multiply the mass of the object times how much faster it's going to go. Okay, so the stronger the force, the greater the acceleration. But do you see where if you applied a same force to two objects, if one is more massive, then it's going to have less acceleration. Does that make sense? Yep. Just kind of eyeballing it. With the same force, the greater the mass, the less the acceleration. Okay. No numbers yet. Like I said, I do have a homework for you to work for that one. Okay, so force is equal to mass times acceleration. Put another way, okay, if something is accelerating, then it is actually exerting a force. If something is, because I'm just kind of switching gears, something that's accelerating is exerting a force. Things that accelerate, I have a couple here. Well, the whole kind of train or bus thing, and also elevators accelerate. So let's look at elevators, because I don't do much with trains. Okay, but if you step into an elevator, it's stationary, right? Its velocity is 0. And let's say you want to go to the 5th floor, so you're going to take a few levels, okay? So it's going to go from 0 meters per second, okay? And it's going to accelerate to because you got quite a few floors to go. So let's just say it accelerates to 20 meters per second, and then it better slow down again before it gets, okay? So kind of like the things you guys were doing yesterday, in kind of your eyeballing it. Let's see. Graph. You guys did really good on that, by the way. Here we have the graph, okay? Acceleration. Can't select acceleration. You would think I could by the time I wrote these slides, and time. Okay. So here, the elevator is on the ground floor. Okay. There's no velocity, and so it's going to have to accelerate up to, let's not go acceleration, let's go velocity. That'd be easier. Okay, so it's going to go from 0 velocity up to, I said, like 20 meters per second. Okay, then it's going to go up to your 5th floor, and then velocity is going to have to go back down to 0. Does that make sense? Let's give it a little more time. Let's make that slope a little gentler. Okay, not so abrupt. So these regions right here, where it's ramping up from 0 to 20 meters per second, and this right here, where it's ramping down from 20 meters per second to 0, okay, these two regions are where we say it's accelerating. Here, it's going faster. Okay, so that acceleration is positive. Okay, here it's going slower. So acceleration is negative. Does that make sense? Decelerating. So my point is that if we look at the force that you're going to feel, I could go ahead and take F is equal to ma, divide both sides. Oh, I did. So the force divided by mass is equal to your acceleration. So do you see where the force we're going to feel a force here, force, I better just do it this way. Force equal to mass times acceleration, leave it that way. The force that you feel as your elevator goes up, okay, is related to the acceleration that you're feeling in the elevator. Now, deceleration or slowing down is also a force. Okay, so the force that you feel here as the elevator slows down to drop you off the 5th floor is equal to mass times acceleration. Here's one for you. I hadn't thought about this, but if you're holding something heavy, okay, the more the mass, the greater the force you're going to, the greater you're going to feel the same acceleration as to somebody who's not holding something heavy. Okay, it's interesting. That's kind of how that works. Put another way, and like if you've ever, it's been a while, but you can take like an elevator up into like the arch in St. Louis. Okay, so once you get going, once you're at a constant velocity, no acceleration, okay, it doesn't really, I can do anything. Okay, that's kind of like when trains get going. You're like, I can walk around, well, but they have kind of this kind of surging back and forth a little bit, but you're like, it's the ramping up to a set temperature. It's the ramping up to a speed and slowing down from the speed that'll get you. It'll get you. Okay, so I've got some figures, again, no numbers here, but so this guy is tugging this cart. The cart starts at 0 speed, and he's giving it a good tug. Okay, and so it's going to go from 0 to a certain velocity. And notice he's pulling with the force F. It has a particular mass, m, and it's going to accelerate with acceleration a. Well, let's say he gets a buddy, and the two of them pull. Okay, notice then, mathematically speaking, if you take 2 times the force, you're going to get twice the acceleration. You scale it up. Okay, notice that the load is the same, kind of 4 little brick things right there. Well, let's kind of change it up, and let's say we'll go back to just one guy, so we're kind of like back to the original scenario, and instead of pulling just one cart of 4 little bricks, he is going to pull 2 carts, so twice as much. Actually, that's going to, it's going to half. Do you see where it's acceleration over 2? It's going to half his acceleration. So that's just kind of eyeballing it. Okay, it's like a direct relationship. Cool. All right. Newton's third law says, and this is where if you have more than one kid, you've probably gotten into the situation where you say, don't hit your sister, she'll just hit you back. That's for every action there's an opposite and equal reaction sort of thing. Okay, but usually we mean forces. So if we think of 2 objects, object A and object B, okay, and I've got some examples coming up, they both, if they're in contact, if one is exerting a force on the other, then actually the other, it may not be so obvious, is also exerting a force on the first one, okay, in the opposite direction, equal in magnitude though. So we could say that like this, like if you have 2 objects, you have one pushing one way, F1, and the other pushing the other way, F negative 1. All right, so this person trying to, well, it looks like they're just stretching out. They're stretch before they work out. Okay, so pushing with, by the way, I don't know if I mentioned this yet, but this will be helpful for you to know. I don't think it's in my notes. But units of force, although there are more than just one, but units of force that are helpful for us in the metric system are newtons. N stands for newtons. Okay, so that might be helpful. A newton is the unit of force we're going to be using. Actually, it's a kilogram meter per second squared, so it kind of breaks down into that. All right, so you see him pushing with 100 newtons, and the wall's pushing back with 100 newtons. It's a wash. If you play tennis, okay, at the time of impact, the ball has a force on your racket, and your racket also has a force on your ball. equal in amount but opposite in direction. Here are couple other examples. They're kind of related. Okay, so if you're a skater, right? So just like this slide shows, you push off, okay, with a force. Okay, so you're going to go this way. The skateboard is pushing this way onto you. So they're opposite in equal direction. And then there's the whole boat thing. Okay, this is why it's harder than you think to go ahead and get out of your boat if you're on the river to get onto land, because as you push, okay, on the boat, okay, this way the boat responds the other way. Okay, so need to talk a little bit about weight and mass. We use them interchangeably, but they are not the same. And the difference between them is basically, if you're kind of a visual person, gravity works on mass to create weight. Okay, gravity works on mass to create weight, basically. So no gravity, no weight. Your weight in outer space, zilch. Your mass in outer space, the same as your mass here. Okay. So mass is constant, regardless of if you're outer space, or if you're on the planet Earth, or if you're on the planet, Mars. So your mass is the same. And units of mass are kilograms, or the fundamental unit of mass is a kilogram. You probably see like grams in the kilograms, but okay. Weight is, like I said, weight only comes about because gravity is involved. Gravity acting on a mass gives us weight. Do you know that gravity is not like entirely understood? Like what makes gravity? And that is so cool. So like physicists are smashing atoms together trying to look for kind of how that works. So units of weight, I don't want to confuse things. Let's see, how do I say this? I'm just going to go ahead right to what the textbooks, how we need to talk about it kind of in physics. A good unit of weight, actually weight, as it turns out, is a force. Weight is a force. And what's the units of force? Newtons. Now you'd be like, oh my gosh, that's not right, because I know I talk about weight in terms of kilograms, but we're kind of, it's fine to keep doing that, but it's not what in fundamentally physics, the unit to use. Okay, so weight occurs when gravity acts on a mass. All matter has mass and occupies space, so all matter then can be affected by gravity and create a weight potentially. So not so surprising though, there is definitely a relationship. If you have gravity, on Earth, definitely something that has more mass will have more weight. That's true. So in a minute on the next slide, and I decided not to have you guys do any problems with this Newton's law of gravitation. I debated. It's just another equation to kind of plug in. But Newton came up, he's so smart, he came up with kind of the relationship between the objects that are being pulled together because of gravity, their masses, the distance between them, and a gravitational constant. So here we go. The F is equal to big G, M1, M2 over R2. Oh my goodness. Now I won't ask you to plug in probably on the test. So far I haven't decided to do that. But all it is basically Okay, let's see. I don't know if I have a picture. I don't think I do. Let's see. Let me go ahead and draw a picture. If you have object A and object B, okay, then what this is saying is that there is a mutually attractive force, okay? They mutually want to collide with each other. That's the force, okay? And it's related to M1, how much the mass here, I almost said how much it weighs. No, mass and weight are not the same thing. The mass of object A, the mass of object B, which is M1, M1, M2, and then R is the distance that separates them. So it kind of makes sense, like the slide says, is that if you increase, let's say if you increase either one of the masses, then that increases your force, okay? But notice that if you increase the R, the distance between them, okay, since you're dividing by R, if you increase R, that actually will decrease force. And that makes sense. If you increase R, if they get farther away from each other, that's going to decrease the force. Now, the one thing I haven't mentioned is that G. And it's kind of neat. In this universe, okay, G has a value of 6.67 times 10 to the negative 11. And those are the units, Newton meter squared per kilogram squared. Okay, that's the value of G. Another universe, I'd like to dream, multiverses, right? That value might be different. So we can actually use this to come up with the force of gravity on objects here on Earth. We just need to know the mass of the object, the mass of the Earth, and the distance between the object and the center of Earth's mass, which would be kind of the radius of the Earth. Okay? We can. We're not going to, but we could. Okay? So now I'm throwing one more variable at you. That little w, the cute little w, is weight. Okay? So we said that weight is a force. Weight is a force. It's basically, you got to have gravity to act on a mass to get weight. Great units of weight actually are newtons instead of kilograms or pounds. So here we go. This actually is a little person up here and trying to figure out maybe how much, what sort of force, what sort of weight they have using Newton's universal gravitation, law of gravity up there. Okay. And again, all they would need to do is M1 would be the mass of the person, M2 would be the mass of the Earth, right? R squared, R raised to the second power, R would be here, the radius of the Earth. Okay. Then W would be in newtons. That would be the mass of the person. Or, darn it, you know what I mean, the weight of the person, sorry. That would be the weight of the person, W. So now we've got two people, or the same astronaut, not drawn to scale, right? Same astronaut standing on the Earth or standing on the moon. Again, when you plug into Newton's universal law of gravitation, of course in this case, both the M2 is smaller for the moon. The mass of the moon is smaller, right? M2 is smaller for the moon, but also R2 is smaller for the moon. R2 being how, if you're on the surface of the moon, how far do you need to go to get to the center of the moon? But with that said, the mass wins out. So look at this. We have an astronaut. This is a good example because I don't know if you could see it, but notice the mass of the astronaut is constant. The mass of the astronaut is constant. His weight varies from, man, I can't even read that. 980, I agree. 980 newtons. Then over here, his weight is, looks like 162 newtons. Okay. So I think the factor I've heard is like 1/6. So basically, because of the lower mass on the moon, also a shorter R, but the lower mass, your weight is 1/6 in general. We could kind of divide that out, but. So this is the picture I kind of tried to draw before. Well, maybe not. So say we have two orbs, okay? One has a mass of 1 kilogram, the other has a mass of 2 kilograms. And notice the little green there is basically the Earth, okay? So they're hovering above the Earth. What this slide points out is actually, according to Newton, there is a mutual attraction between those two orbs, okay? But it's that force of gravity between those two objects is nothing compared to the force of gravity that both of those objects feel with the Earth. That's what that's showing. So again, kind of like the astronaut, notice that they, well, I guess they're different orbs. So they have different masses, so they have different weights, period, end of story. Okay. Any questions? Let's just kind of eyeballing it. All right. Dun, dun, dun. So we got to the assignment slide. Okay, so chapter 3, I'm going to pull these up on the internet, hopefully. You see your name there? Let's see. Home. Home. But the first one is, you don't need to use a calculator or anything. And then the other two